Good morning. So we begin the first guest lecture of the event with Dr. Balaraman Ravindran sir's talk on Relational Representations and Reinforcement Learning. Dr. Balaraman Ravindran is the Mindtree Faculty Fellow and a professor at the Department of Computer Science and Engineering and the head of Robert Bosch Center for Data Science and AI at IIT Madras. He completed his PhD at the Department of Computer Science, University of Massachusetts, Amherst. He had also worked with Professor Andrew G. Bartho on an algebraic framework for abstraction and reinforcement learning. His research interests span the broader area of machine learning, ranging from spatiotemporal abstractions in reinforcement learning to social network analysis and data/text mining. Much of the work in his group. This is
There's echo, right?
yeah. I think it's better now.
Ravi, maybe you can start. There's some echo.
Sure. Can people hear me clearly, or is there an echo still?
It is clear.
It's clear. Okay, because I'm not able to hear. I mean, I'm hearing my voice back. That's why I'm a little worried.
So I think if everybody else mutes, there shouldn't be a problem.
Yeah, if all of you can mute other than me, that'll be good. And now we can try again. Yes, that's perfect. So good morning, everyone. I'm pretty sure all of you are coming off the fantastic talk. So one thing, a caveat, even before I start, I'm not going to talk about neuroscience today. And this is something Srinivas and I talked about, and he said, it's fine, you give a purebred AI talk. So that's exactly what I'm going to do. And okay, so this is a collaborative work with a bunch of people. So the primary drivers of the work were Ashutosh Kakadia, who is an MS student here, who is graduated since then, and Arjun Manoharan, who was an MS student here again. Both have graduated. And Harsha, who is a PhD student at UT Dallas, working with my collaborator, Sriram Natarajan. And his advisor, Dr. Prasad Thadepalli from Oregon State, was also part of one of the projects that I will talk about today. And just moving on. So the main theme that I'm going to talk about today is reinforcement learning, right? And I also noticed that there is no real RL talk at the meet. Is it correct, Srinivas?
Yeah. You are the only RL that should talk.
Okay, so what I did was I added a few slides on introducing what reinforcement learning is at very, very high level, very conceptual level. Promise no equations. Okay, at a very high level, I've tried to introduce what reinforcement learning is, and therefore I did a little bit of plastering of the rest of the talk. So I in my abstract, if anybody had seen it, I was going to talk about 2 papers. Today I'll try to limit it to only 1, and perhaps if time permits, I can talk about the other paper. I have slides for it. But my goal today is actually going to be to introduce you to RL, and then perhaps talk about one of the papers that we worked on. Right? Moving on. Right. So some of you might be familiar with a lot of different models of machine learning, right? Supervised learning, unsupervised learning, semi-supervised learning, and so on and so forth. Mostly, machine learning is all about learning from data. So I'll give you a collection of inputs. Right, and I'll tell you what the right output is for a given input, right? So given the input, I'll tell you what the output is, right? So this is how the data is presented to a machine learning agent, right? And then the agent learns from these, labeled examples what to do with unseen data points, right? This is one kind of problem. So other kind of problem is I give you a lot of data points. Can you find out some patterns in them? Okay, there are like 3 groups of people among my customers, things like that, right? So the question that I typically ask people, so the first form of learning is called supervised learning, right? And the second form of learning is called reinforcement learning. Okay? So in supervised learning, you basically have, sorry, I got distracted with a lot of pop-up messages. So the first form of thing is called supervised learning. where I tell you what is the output you should produce, right? And second form is called unsupervised learning, wherein I just have this request. Is there a way to stop all these pop-ups that tell me when people are entering and leaving the meeting? It's very distracting. Because it looks like a lot of people are dropping off and coming back, and then there is this continuous stream of pop-ups on the screen.
I can unmute. I can mute the sound. It creates a beep sound.
The sound is muted. Sound is not there now. Sound is gone. Yeah, because there at the beginning, the sound is gone, but the pop-up, it just pops up at eye level, right? It's
right.
Yeah, sorry. Right. So give me a second. Okay, I'm back. So in supervised learning, basically, you're told what is the output that you have to produce. And in unsupervised learning, nobody tells you an output. You're just trying to find some patterns in the data, right? So let's come to the problem of cycling. So how did you learn to cycle? Was it supervised or was it unsupervised? So people actually give me both answers. Right? Some people say it is supervised because there is a parent somewhere near you, and some people say it's unsupervised because the parent is really not telling you how to cycle. In fact, it is neither, right? Because you're not learning from prior data. You're actually getting on the cycle and trying out things, right? And it's not unsupervised learning, because unsupervised learning is only about finding patterns, not about producing outputs in response to a stimulus. But here you have a stimulus, right? You have your feedback that is coming from the cycle, and therefore you have to produce a response to that stimulus. So it is not an unsupervised learning problem. And it is not a supervised learning problem either, because nobody is giving you detailed instructions. If at all you're getting any instructions from an adult, it is something along the lines of, hey, be careful, right? Don't fall down. Ring the bell or something like that. I mean, you get very, very high level feedback from the person. They are not telling you when you have to push with your right leg, when you have to push with your left leg, whether you have to lean one side or the other. All of these things you kind of, get some kind of a sense by your, just your feedback, your sensory mechanism feedback, right? And then you somehow decide that, okay, this is the right policy to do. You are getting some feedback. If you cycle well, the parent or uncle or somebody will say, hey, good job, fantastic. They'll clap and say something, right? If you cycle badly, you'll fall down, you get hurt, right? So you get some feedback, right? It's not that there is no feedback from the environment as to how you are doing. But the crucial difference between supervised learning and reinforcement learning is the following. In supervised learning, I give you the feedback beforehand, right? I tell you that, hey, if this is the input, this is the output you have to produce. Now, your goal is to mimic what I have given to you. So this is like learning from instructions. Somebody tells you a priori what to learn, right? And then you're going to learn that. In reinforcement learning, what do? You first try to cycle, right? You try to do something, right? You fall, you lose your balance or something like that. Then somebody gives you a feedback, like falling down or somebody clapping. So all of this comes after you try to produce an output. So this is in some sense like an evaluation. Okay? So in supervised learning is like learning from instructions. Reinforcement learning is learning from evaluation after you have tried things out. And that's what you have to try out different things to make sure that you get the right output. Sometimes you may get something that is partly correct and you wouldn't know. So you still have to keep trying things until you get to the right solution. So that's why we call reinforcement learning as learning through trial and error as well. And it's just not limited to cycling, right? If you think about it, right, all kinds of learning. And in fact, if you look at babies learning to walk, it's all about reinforcement learning. Right? They fall down, get hurt, and you need that feedback. And luckily, babies are made of rubber when they are young, so they just bounce back up and then they start, walking around after that. So it's all fine, right? And same thing, even something like talking, right? So babies normally will just be babbling around, and they say something that randomly sounds like mama, or papa, or something like that, and all the adults around them go crazy. They clap and say, "Hey, fantastic job!" Right? And then people say, "Oh wow, okay." The baby thinks, "I have made all the adults, look at me. That's all the feedback I want. That's all the reward that I want." Okay? So, and then it keeps trying to, slowly refine its vocalizations, right? So that's how these things work. So I'm going to tell you what RL is with the example of Tic-Tac-Toe. Right? Very, very simple example. I hope most of you know what Tic-Tac-Toe is. You have to get 3 pieces in a row. You take alternate turns, and you're operating on a 3x3 square, right? Oops. And let's say that I will train you through supervised learning. How will I do this in Tic-Tac-Toe? So what I will do is I'll give the learner certain board positions, right? I'm giving you, like here, I've given you 4 example board positions, and I'll also tell you what is the move that an expert will make, right? So I'll tell you, okay, if this is the position, right? If this is the position, then you have to make this move, right? If this is the position, then you have to make this move. So I'll give you these instructions beforehand, and from these instructions, you have to learn how to play the game, right? But the reinforcement learning way of playing it is to say, hey, go and play the game, right? Go play it against some opponent. If you win, I'll give you 1 point. If you lose, I'll give you -1. If you draw, I'll give you 0. And how do I learn now? I just repeatedly play games, right? And then I keep getting 1, -1, and 0. And then finally, I figure out how to play the game eventually. So is it even possible? So let's give you a very simple way of thinking about it. Let's say that's a game that I have played on the top, right? So you can think of it as like a path to this tree, right? Then you can see at the end, what has happened is I have won the game, right? I've gotten 3 X's in a row, so I'll get a +1. So what I can do in this case is go back to all the positions I have seen so far, right? And say that, hey, look, from here, if I put an X here, right? If I put an X here, that's a good move. So in this position, so I actually, it will lead me to a win if I put a X at the top left corner, right? So let me make sure that I put the X more often in the top left corner than any other moves that I want to think of. So like that, right? So every move that I play on the way to winning, right? These are good moves. So I'll increase the chances of playing that move again. I'll increase the probability that I will play that move again. Suppose I had lost the game. What would I have done? I would have gone back, decrease the probability of all the moves. Okay, next time, okay, I played it now, but next time I'll play it with even less chance, right? So like that, I keep doing this repeatedly. Whenever I win a game, I increase the probability of all the moves I have taken for winning the game. Whenever I lose the game, I decrease the probability of all the moves I have taken for losing the game. So eventually, I'll only be playing moves that lead me to win the game. Right? This is assuming I'm playing against a poor opponent, right? Because if you're playing against an ideal opponent, you can never win. So what would I do if I draw the game? I just leave the probabilities as it is, right? That's a simple enough thing. I hope people got it, right? I mean, it's hard for me to get feedback here. I think you understand the basic algorithm. This is a perfectly valid algorithm. This will work. And if you know how to write code, you can code this up and you can make it learn to play Tic-Tac-Toe. Okay, there are a lot of problems with it, but as a functional algorithm, this is fine, right? And as long as you're playing Tic-Tac-Toe, it will work. More complex problems, it will run into all kinds of complications. But here, let me ask you this question. Right? Look at that position. Now, if this is a position I encounter in a game, do I need to play till the end of the game and get 3 X's in a row to know that I have won? Right? Can someone unmute themselves and say yes or no?
No, sir.
No, sir.
Because at this point, I have won the game, right? Because there's nothing that O can do that to stop me from getting 3 in a row. Daily. So in such cases, I don't have to really wait till the end of the game. As soon as you see a position like this, I can go back and change the probabilities of all the moves that got me here. Right? So basically, if you see a position like this, put a X there. If you see a position like this, put a X here. If you see a position that's all empty, put a X in the middle. All of these moves, I can increase the chances of making those moves next time I play the game. Right? I don't have to wait till the end. Right? So that's a rational thing to do, right? So how did I know that this is a winning move? I've not gotten 3 X's in a row because that was the definition of getting a +1, right? But how do I know if I come to this position, I'll get a +1? It's because you know the rules of Tic-Tac-Toe, right? You can play it out in your head and say, hey, look, if you're already in this position, there is no way that guy is going to be able to win. But that's because you knew the rules of the game, and the rules of the game were simple enough so that you could actually reason about this board position and figure out whether you have won or not. So that is fine for Tic-Tac-Toe. What about more complex problems, right? What about things like chess or even riding the cycle, right? So how do I know that whether I'm doing the right thing halfway through or not? So here is where we take advantage of the fact that we are playing this repeatedly, right? So what do I do is, for every position, I'm going to keep track of what fraction of the games I won from that position onwards, right? So from this position, I probably won, say, 95% of the games. So something happened another 5% of the time, right? But then maybe from the previous position, I would have probably won, say, only 60% of the games, because I tried making some other move. So whatever happened, right? I won like 60% of the games. So now what has happened is, I've gone from a position where I won 60% of the games to a position where I won 95% of the games. Now I don't have to go and play till the end, right? Just these two positions, I can just look at the two adjacent positions. So one where I won 60% of the games, one where I won 95% of the games. So obviously it is a good move, right? Going from 60 to 95 is a good move. So I can actually increase the probability of that move, okay, because it took me from 60 to 95. But suppose I was in a position that gives me 60% chance of winning. Now I move to a position that gives me only a 30% chance of winning. Bad move, right? So I'll decrease the probability of making that move again. So I don't have to wait till the end, right? All I need to do is just see what the next position is, right? It takes a while for me to, learn those probabilities of winning. But once I learn the probabilities of winning, I don't have to wait till the end. In fact, I can do this from the beginning. It turns out mathematically everything works out fine. Even if I do this from the beginning, when I don't have a good idea of whether I'll win or lose, I'll still converge to something useful, right? I'll converge to the optimal policy, optimal way of playing the game in most circumstances. In fact, I can go further. Okay? How did I know what is the fraction of games that I won? Because I waited till the end, right? And then I saw whether I won the game or not. Suppose I played 100 games and I see this board position in 50 of them, and in 45 of those I won, right? So then I'll say win percentage is 90, right? But then I don't have to wait till the end, right? So if I move from a position that has a 60% chance of winning to a position that has a 95% chance of winning, then I can also increase the chance of winning from the previous position, because I know how to get to a position that has 95% chance of winning now, right? So now I can change the way I play. It is a little more subtle, but I can change the way I play so that I can increase the chance of winning from 60 to 95. Because if I play that move all the time, then the chance will go from 60 to 95. So this idea that I'm going to look at the winning chances from the next board position and use that to update both my current winning chances as well as the probabilities of the moves I'm going to make, right? This idea is called temporal difference learning, and was proposed by Andy Bartow, Rich Sutton, and Chuck Anderson back in 1983. Around the same time, backpropagation came in, but TD took a much longer time to become popular in AI. But in neuroscience and behavioral psychology and other areas, people have been looking at reinforcement learning almost since the 80s, right? So it's a very simple rule, but it can profoundly explain very complex behaviors, right? And has had a lot of impact, not just in AI and machine learning, but also in psychology, neuroscience, and other related fields, right? So I can pause here, not stop, and ask people if they have any questions.
Hello.
Yeah.
Yeah, so in like Tic-Tac-Toe, it's like you encounter the same position like a lot of time, but in chess and other games, you don't like the position itself is new like every time you play the game. So how do you do that in chess or
In
something?
chess, I mean, it's not always 100% new, but maybe you do encounter the same positions quite often. But I see your point, right? So the point is, hey, in tic-tac-toe, it's very easy to remember, what is the positions. You can enumerate the positions that you looked at, right? So this is why you look at what is called function approximation, right? This is, I mean, nowadays people do this with deep learning a lot, and so you look at this called function approximation, where you not only learn about one board position, but whatever you learn for that board position is also applicable to things that are similar, right? With chess, it's a little tricky. You have to look at very high level things like, okay, do I control the center four squares? That's a very important feature in chess, right? how many pawns that I have, what is my piece superiority. So those kinds of things, not just the exact location of where you are at, right? So you have to look at more higher order features like that in order to do this generalization from position that you have seen to positions you haven't seen. In fact, it's even worse in cycling, right? I mean, cycling is a continuum, right? So I can be traveling at some velocity in a particular range. I can be leaning in some angle at a particular range. I can have my steering, my handlebar in different angles, right? These are all real numbers. So I can't just index real numbers into boxes, right? I mean, I'll have to have some way of approximating it. So that is something that is very widely done. Yeah.
Okay, thank you.
Okay. There are no further questions. I'll move on. I think we have about 10 minutes or so left, right? So reinforcement learning works, right? There are a lot of success stories. You might have heard some of the game playing success stories that are there, and recently there was this thing with protein.
Sorry, sir, I had a question.
Yeah, sure. Go on.
So Unmesh.
Yeah.
Yes, sir. So I was saying that in the case of tic-tac-toe, we have a goal state to which we want to reach.
Yeah.
And that is with respect to the winning thing. And if I have sufficiently read about it, there's a condition when no one can win, which would be called an impasse.
Yep.
So similarly in chess, there is a situation where you would be going to a situation where there would be a repeated draw, or like threefold repetition or something.
Yep.
So that should look like an impasse which cannot be resolved without one compromising with their best positions.
Sure.
So I think that the previous question also, just wanted to extend that point. That probably
they're very different questions,
that
actually.
Exploration is also an impasse sometimes.
They're very different problems, actually. What he was asking about was, exploration, question of exploration. What you are asking about is the question of, how to shoot for the right right target, right, in terms of the reward functions, right? So it varies. That's why I said that your tic-tac-toe opponent had to be, guys, I mean, somebody has to mute themselves. That's annoying echo.
Yes, so it was like, what target would we want to take?
Yeah. You define the problem. Like in the tic-tac-toe case, I said you get a +1 for win, you get a -1 for loss, you get a 0 for drawing. So obviously you would prefer to win over draw, right?
Yes, sir. Yes.
So that's the thing, right? So you're trying to get more as much feedback as you can as possible. Therefore, you'll try to win, right? So it depends on how you design the feedback systems.
Yes, sir.
So that reward design is very much part of the problem setup.
Yes.
Okay, fine. So let's move on. So we have less time. I'm going to blitz through the second half of my talk, but bear with me with that. So there are a lot of success stories you have for RL, a lot of game playing, protein folding. I'll talk about it on later slide. Even things like flying helicopters, getting robots, and managing the power system in a very big data center. A lot of different applications where RL has been successful. But RL success is not new. So that's a picture of Arthur Samuel playing checkers with IBM live on TV, right? This is back in 1950s. So and the checker playing program was actually using reinforcement learning, even though it was not called reinforcement learning back then. We kind of know that it is what it was doing was reinforcement learning, right? So, and of course you have had other success stories like AlphaGo, which beat the strongest Go player in history, right? And then comes AlphaFold, right? I mean, all of this game playing is all nice, but then you come to something like this, right? Protein folding, as many of you know, is one of the hardest problems in biology. So sometime back, there was this announcement, an AI agent achieved a near perfect score on all the known structures in predicting all the known structures, right? So that was based on a reinforcement learning engine called AlphaFold, put out by a company called DeepMind. And this kind of seemed to accelerate the development by several decades. And then this case now, very recently released the protein structure database that was predicted by AlphaFold. Not only that, they made it available publicly on their compute platform, right? So if you are using Google Colab, you can actually access these the AlphaFold database directly from there, right? So now people are started talking about, hey, should we declare this problem as solved? I don't know. I still don't buy it. But still, I mean, the point has come where you can stop worrying about protein structure prediction and start using the predictive structure because many people are confident that these structures predicted are quite right. So I think that's a huge change that reinforcement learning has brought about, right? So reinforcement learning, again, like I said, huge excitement. That's the exponential growth of papers on RL that is being published, right? But then the end of the day, right, I still am learning associations from data. And for me, learning associations from data leaves the model fragile. Right? It doesn't really, make it. So if you come across something that is unseen before, you're going to have trouble. So here is an example. So here is a goal, like a football agent that learns how to score goals, how to defend the goal, and things like that. Right? You can see that the blue guy has learned reasonably well to score goals. Eventually, see that he gets better and better. Right? So he gets better and better. But then, what happens when the goalie becomes slightly adversarial? How do I go to next? There you go. See, the goalie now just falls down and starts, like he's crying. And this blue guy gets completely confused. Gone. So the same blue guy who was scoring goals, right, in the previous video, now he's getting completely confused because this goalie has decided to do something which the player has never seen in its training, right? And so if it's a human being, you would have known, right? That guy is falling down. I have an easy way to score a goal, as opposed to tap dancing all around the place and then sometimes even leaving the ground. It's getting confused. That's why I said reinforcement learning is still fragile. So we need to go beyond whatever has been done so far, right? So my thrust of what I was going to talk about today was that we need to integrate reinforcement learning with more ideas from classical AI. People talk about logic, they talk about symbols and talk about semantics of what is you seeing in the world, right? And looking at abstractions, both spatial and temporal abstractions. The humans use all of this extensively, right? When you are trying to do higher level reasoning about decision making, right? So, So what I was going to talk about, so I'll probably, Srinivas, is it okay if we don't talk about what I originally said I'll talk about?
Yeah, you have another 3 minutes.
So I'll just stop with one or two slides. I'll completely skip what I was going to talk about.
Sure.
So I thought this might be more useful. So what our goal was to set up, using what is called relational representations in reinforcement learning, right? And to make RL more interpretable, the policies more understandable by a human being, right? So that the human can start giving you feedback. Okay, don't do it like that. You should do something different. Right? And so you can interface this whole thing with classical planning frameworks where you use logic, first order logic, and you reason about events that are there in the world, and then you use reinforcement learning on top of it. So that's basically what we were trying to set up. So the relational representations is now becoming more and more common, right? Whether you are looking at bioinformatics, biological data, or whether looking at transportation systems, communication networks, social networks, everywhere you're getting more and more data about not just entities but relationship between entities. So none of the entities you talk about in these domains are independent by themselves, right? You can't treat them as single vectors. Talk about these things interacting with one another. So for example, a congestion in one intersection in the city will probably affect the congestion in other intersections in the city. So I can't just say I'm going to look at which intersection is likely to be congested in isolation. So I'll have to do this jointly, right? So this is basically why people are going towards more and more of these kinds of relational representations. And so here is an example of how it will look like, right? So instead of talking about a single entity, I'll talk about, okay, the movie. There is a movie, and then there is a director, and the producer, studio, actor. All of these are independent, different entities, right? So there is a relationship between an actor and the movie, right? Or if you can come to publication, there is a paper, there are authors, publishers, editors, books, journals, where it appeared. So you can see this, right? A paper is authored by somebody. A paper cites another paper, so there will be more such papers, right? And then there will be multiple papers that are authored by the same author, and multiple papers that appear in the same book and journal. So what we typically do in normal learning scenarios is that make all of this into a single vector, right? just repeat the author 100 times. For if he has written 100 papers, you'll repeat the author's name 100 times in your database. As opposed to that, this kind of relational information allows you to learn not only compact things, but also the relationships between them. Say, hey, two papers are connected because they cite one another. They are authored by the same person, right? They are published by the same publisher. So all of these things, you can get these kinds of relationships from the data. And learning with this kind of a rich relational data allows you to make your learning more understandable to a human. And so there are many ways in which we can tackle this. And so what I'm going to do, I was going to talk about two different pieces of work, one on online learning and one on doing a unified framework, but unfortunately, I can't do that. So let's go here, right? So for me, deep RL has revived excitement in the community, but many fundamental questions still need to be addressed, right? This is basically repeating what I said earlier. And learning associations from data leaves the model fragile. So I'm saying we should go look at more classical AI. There are other people who are saying we should just make the neural networks, deep neural networks that we use more robust, and that will help us. So I think we should do both. And so that's basically it. And if you want to know more about what we do at our center, please check out our webpage. Right? So, and we're all on all kinds of social media. Cool. So, any time for questions?